Assalamualaikum warahmatullahi wabarakatuh. Nama saya Muhammad Syamuddin bin Muhammad Zaki daripada BEEA Section 1/2. Dan pada hari ini saya akan bentangkan assignment control untuk BEEA 3393. Okay. Ini adalah soalan saya. Question dia S plus 6 S plus 1 bracket S plus 2. So what we need to do is first we need to find the angle and the intersection of a asymptotes. Here is first thing is cari poles and zeros transfer function. Kat sini kita punya poles ada 3, 1 dan 0. Kita ada 1, ada kosong. Kosong. Dan kita kena cari the asymptotes intersect real axis. Ini adalah calculation untuk dia. Negatif 6 tambah negatif 1 tambah negatif 2 bahagi poles tolak 0. So poles tolak 0 3 tolak kosong. So punya asymptote intersect at real axis is negatif 3. Dan the asymptotes radiate out with angles which the K is 0, 1 and 2 because there is 3 asymptote lines on the root locus. So first we get the 60 degree, second is 180 and third is 300 degrees. Okay, this is the solutions for the part 1A. Then for the B, determine the breakaway point. This is the solution for the breakaway point by using the transfer function given. Then I get the root locus breakaway point at negative 1.27. This is derived from this equation. Negative 3s minus 18s squared minus 18. That's for the breakaway point. Find I determine the omega. Determine axis at crossing points. So by using a root Hurwitz criterion, we can find the value for the j omega. As we see, this is the transfer function that was given. Was from here. Yeah, from here. Then we apply it to the Hurwitz criterion table. After that, after do some calculation in this, only the S to the power of 1 row can yield the row of zeros. Thus, the 200.04 minus 9k over 16.7 equals to 0. Then we can get the k, which is the gain, to 22.23 by using the s to the power of 2 row with k 22.23, we can get this equation, 16.67s squared plus 22.23 equals to 0. Then from here we can get the value of s plus minus j 1.15. So the root locus crosses the j omega axis at plus minus j 1.15 at the gain of 22.23. Okay, next is draw the root locus on the graph paper. Okay, this is the root locus that I draw on the graph paper. First, we see the poles. Our pole is, as we can see, our pole here is -1, -2, and -6. So here is the pole -1, -2, -6. And then the intersect real axis, and the intersect the real axis is -3. So at the we plot the -3 here, and then draw out a 60-degree line and 300-degree line here, which is uh, the asymptote line. The dotted line is the asymptote line. Okay, then we need to find the breakaway. Our breakaway is -1.27. So we need then we find at the graph that we draw, we need to find -1.27. So this is the crossing point. I mean the intersect point. Sorry, intersect point. And then we need to find the cross section for this one. For that one, we can get from this the axis as crossing point by using the Ruth-Hurwitz criterion table. We can get the crossing point for the j plus minus j 1.15. So we plot here 1.15 and -1.15 here, and then we draw the root locus from this point, from point 1.15 long, and then go through the intersect at the real axis, which is the -1.27, and then continue it to -1.15. Alright, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hazan Firdaus dan Muhammad Azli. Okay, today I will explain about for the second question. Okay, for this question, second question is determine the steady state error of the system. Okay, so this is our transfer function. So first we need to factorize the transfer function. So we can get like this. We will get k over s plus 1 bracket s plus 2 bracket s plus 10. Okay, so how we do? Okay, so we use the formula to find the gain. Okay, for the dominant poles, it is given in the question, which is -1.37 plus imaginary 1.4. Okay, so for the gain, we just take this denominator, then we use the dominant pole and substitute. So after we substitute, we will get the gain is 19 19.436. Okay, so this is the gain. Then we will find for the KP. This is the value GS limit GS HS. So we take the gain 19.436 and divide by the denominator S plus 1, S plus 2, S plus 10. Then the value net for the gain is 0.9718. Okay, so lastly we will find the steady state error as the question mentioned, request. So the value is the formula is 1 over 1 plus KP. Okay, so the value for KP we already get, so just substitute and that's all. So we will get 0.5072 for the steady state error. Okay, so next for the question B. Okay, we see what is the question B one. Design a controller so that its steady state error for step response is reduced to 0 by remaining the existing damping ratio. So let the value K1 equals to 1. Okay, so for the controller we will use the PI controller to improve the steady state error to 0. So the formula is GPI S. So this is the formula. Okay, so the question given K1 equals to 1. We will let it. So the K2 we will use 0.01 because the zeros that is the close one to the origin. So this is the value that close to the origin. So GPI controller, so 1 bracket S plus 0.01 for the K2 and K1 over S. Okay, so after that we got GC. So we take S. This is GS. S plus 0.01 over S. Okay, so that's after that we will K bracket S plus 0.01 and over S. This one is the denominator. For the just now we get S plus 1 bracket S plus 2 bracket S plus 10. So after we calculate, we will get that proof that the ESS for the steady state error is proven that is equal to 0. Okay, so that's all from me. Thank you.